with Zhongwei Zhou presenting on computer effectiveness, cost-effective, computer-aided diagnosis of lung cancer and chest CT. As a little background for Zhongwei Zhou, Zhongwei is a PhD candidate studying, getting a PhD in biomedical informatics at ASU. He has some impressive experience working in various areas of deep learning and computer vision. His research really focuses on developing novel methodology that will minimize the annotation efforts for computer-aided diagnoses, therapy, and surgery. He's had 10 or more peer-reviewed publications, and today he's going to talk about his most recent work. Thank you, Zhongwei.
Hi, can you hear me well?
Yes, we can hear you.
Okay. Thank you for introduction. Greeting everybody. My name is Symposium Zhou. I'm a PhD student in ASU. And today I'm talk about the cost-effective deep learning in medical image analysis. Deep learning is getting more popular than ever. It does not require design handcraft feature for specific imaging task, but automatically learn the image feature in an end-to-end manner with the use of deep neural network. Deep learning has huge impact in healthcare. It can achieve human-level diagnosis of most common disease, such as lung cancer, diabetic disease, and skin cancer. However, training a deep model needs a huge amount of annotation cost. What is the annotation? As an example, to train a deep model for lung cancer detection, the human expert have to tell it where is the nodule, how big it is, and whether it's benign or malignant for every patient CT scan. To achieve a human-level lung cancer detection, more than 42,000 CT images should be annotated in such a way. Similarly, more than 120,000 images are needed to annotation to detect another disease. As you can see, annotation is a very important factor for the success of deep learning in most common disease. The question is how to develop effective deep learning algorithm for those diseases without so many annotation data. It is very important to quickly develop a useful deep learning system, especially, for example, COVID-19. It is an emerging and rapidly evolving outbreak situation. A flood of patients are waiting for diagnosis result during such an outbreak. And doctors have no time to annotate every cases in a short span of time. And there were not too many doctors at the beginning actually have expertise for novel diseases. Here I show you the simplified workflow about how deep learning engage to the healthcare in practice. First, we obtain the annotation from a human expert, and then train the model using this annotation. Finally, deploy the deep model in clinical practice. Perhaps some hospitals lack of expertise. To optimize this workflow and to quickly build an effective system, our research goal is to exploit novel method to minimize the manual labeling effort. I will specify 3 aims. First, select most necessary images for annotation. Second, develop advanced deep neural network architecture with existing annotation. And finally, extract generic knowledge directly from the unlabeled images. To validate our 3 aims, we have used 9 different user cases, including disease detection, segmentation, and classification. In the following, I will present you the progress that we have made for each of the aims. The first aim is to select necessary samples for annotation. Medical images are generated every day. With limited budget and time, it is infeasible to annotate each and every clinical image. So we try to find an important subset of image for human expert to annotate. The common approaches is called human in the loop active learning procedure. It incorporates both human expert and the deep model together to precisely detect a disease. Given a pre-trained model, we test it on the unlabeled image and get the prediction. And then select the most important image based on the prediction. We send these images to human expert for annotation and merge with labeled images. Using the labeled images, we fine-tune the model again and get the prediction from the new model. And then we select the most important image again for annotation. As you can see, it is a loop. The key challenge in the loop is how to select the most important cases. For example, we have adopted two major symptoms for COVID-19 and classify subjects into positive and negative groups. Here, A and B are unlabeled subjects. Given the limited budget, which subject would you prefer to annotate first? If we look at A, it can already be classified into the positive group by the current model. Therefore, we do not expect a major change of the decision boundary when labeling subject A. However, subject B is more ambiguous to the current model. Whether it is positive or is negative will dramatically change the decision boundary. So if we randomly select the sample for annotation, as the annotated data increase, the accuracy of the model will gradually increase as well. If we only consider the most important sample to be labeled at first, we call it active selection. Active selection can quickly achieve high accuracy with lower number of annotation. This gap represents the amount of annotation cost reduced. We hypothesize that wisely select the important samples can dramatically reduce the annotation cost. Our previous study have confirmed this hypothesis. Here, the solid line is active selection, and the dashed line is random selection. We concluded that by using our active learning method, the annotation cost can be reduced by more than 60% compared with random selection. So this work advised that not all data is created equal. Our job is to find the most essential data that can increase the deep model performance with as lowest annotation cost as possible. After collecting certain amount of annotation, the second aim is how to develop advanced deep neural network architecture. Better architecture can lead to higher performance in disease classification, detection, and segmentation. For this aim, we focus on segmentation tasks that partition an image into multiple pieces to clearly localize both organ and lesions. Image segmentation helps quantitatively measure the size of the lesion and make the surgery more precise. When we collect the annotation for segmentation task, for example here, select a cell. The human expert must draw the contour for each object. The most popular architecture for image segmentation is called UNet because it looks like a big U. The input is the original medical images, and the output is the segmentation mask of the target object. For example, here, the liver. The encoder will map from image space to deep latent feature, and the decoder will map the latent feature back to the segmentation mask. As you can see, the model extracts different level of image feature. We hypothesize that by aggregating multi-scale feature can lead to powerful model for image segmentation. Not only just the level 4, but also consider level 3, level 2, and level 1 features. We devised and advanced the architecture based on the original UNet. We call it UNet++, because it offered two notable innovations. The first innovation is redesign the skip connection to encourage a different level of image feature aggregation. And the second innovation is introducing deep supervision. In contrast to the original UNet architecture, UNet++ provide additional supervision for every level of image feature, so it achieves higher segmentation accuracy. We evaluate UNet++ on 5 image segmentation tasks, including neural structure segmentation, cell and nuclear segmentation, brain tumor, and the liver segmentation. The red bar is UNet++, and the gray bar is the original UNet. Statistical analysis shows that our UNet++ significantly outperform the original UNet on every task. Generally speaking, collecting annotation for segmentation task is extremely time consuming because, for example, to segment the nuclear from an image, the human expert have to draw contour for each and every nuclear. To make it more efficient, instead of annotating all the objects in the entire image, if there is a way to select the most important region for human to annotate and the rest can be done by the machine, it will be great. This procedure can be optimized by our unique architecture design of UNet++. Because the four branches in UNet++ can give the annotation suggestion for each pixel in the image simultaneously. Deep neural network learn visual representation through multiple semantic levels. This study advises that we must fully utilize each and every level of representation for a more precise and comprehensive result. So far, we have only discussed how to use the annotated data, but it is also important to recognize the power of unlabeled data. Therefore, my third aim is to extract the generic knowledge directly from it, so that the deep model can transfer this knowledge to many other image tasks. Now, how to extract this generic knowledge? We observed that medical images are embedded with consistent and recurring anatomical structure. So we hypothesize that using this information, we can empower deep models with generic and transferable image representation. Here shows the diagram of our proposed framework. We designed it as the simple image restoration task. Given an image, we first deform it and then feed it into deep model. Let the model learn how to restore the original image. To deform an image, we propose 4 different image transformation approaches. Each of them allows the model to learn from different perspectives. For example, it can learn from organ appearance, organ texture and local boundary, and organ spatial layout and geometry, and many more. We found that learning from multiple perspectives can help to build a generic and transferable models. Actually, we are the first one to build the generic pre-trained 3D model for medical image analysis. We call it Models Genesis. It learns representation directly from image without any human manual annotation. and it leads to powerful target model for many medical imaging applications through transfer learning. Model's genesis shows higher precision and more robust performance than existing method on 5 medical applications, including lung nodule detection and segmentation, and pulmonary embolism detection, liver, and brain tumor segmentation. We pre-trained this model genesis on more than 800 chest CT images, and then translate the image representation to different target applications. Model genesis is also an annotation efficient method because for every task, as you can see, model genesis can achieve the same accuracy while reduce at least 30% of annotation cost. We have observed that model genesis show good generalizability within the same image modality. That is, if the model is pre-trained on chest CT image, it is more beneficial on the target application that is in the chest area and in the CT modalities. In the future, we intend to collect medical images from different modality and pre-train modality-oriented models for improved accuracy in that particular modality. And moreover, we intend to collect medical images from different body parts and pre-train organ-oriented genetic model for improved accuracy in that particular body part, such as genesis lung, genesis liver, and genesis brain. We made the development of model genesis open science and invite researchers around the world to contribute to this effort. We hope that our collective effort will lead to the holy grail of model genesis, effective across disease, dataset, organ, and modalities. To summarize, the main point of my research goal is reducing annotation cost. Each aim specifically focus on the component in the workflow. Select important sample for annotation, develop a powerful model with annotation, and extract generic knowledge directly from the image. Altogether, we build a competitive model using small amount of human annotation. I would like to thank my advisor, Dr. Liang, and all my thesis committee professor. This research is supported by NIH, ASU Mail Grant, and the Mail Innovation Grant. And thank you for listening. I'm ready for questions.
Thank you, Xiangwei. This is a great topic. I've seen this demonstrated in a lot of different research conferences. I'm curious with this, as we're waiting for, please, I encourage everyone to, if you have a question or something that's relevant to it, to please type it in the question answer section and we'll be able to get to it. With this medical image analysis, how have you seen this adopted in actual of healthcare?
I'm sorry, how can I see what?
How have you seen this adopted or translated from research into healthcare practice? Because the value that this offers is quite great, right? More cost effective in sort of guiding efficient identification for diagnosis and treatment. How have you seen this adopted in healthcare practice now?
According to the news that I see, actually, in China, there is a lot of tool developed from the deep learning and already used in the hospital and also in the personal phone. For example, the COVID-19, it's a very popular disease now. A lot of hospital already use the computer-aided diagnosis to do this kind of study. And also another example is the skin cancer, which is I see a lot of tools already built into the smartphone, and the patient just find something wrong in the skin, they take a picture, and the machine will like give you some suggestion. So what's wrong, or if it's wrong, I suggest you go to the hospital, and if it's maybe it's just benign. So some application already there.
Right. So because you benchmarked your process to some other processes that are out there. So is the intent to an algorithm or a method like this would then be incorporated into standard radiology practices that would slowly improve upon previous versions?
Mm-hmm. So let's say the workflow I showed before, if we build a model, let's say, okay, here, if we build a model, then this model can be like installed. If the old agreement is done, it can be used in the, like, for example, CT scan. And then it's not just to give you a CT scan. The machine will simultaneously give you some attention, like, hey, maybe this area is more weird, more chance to have some disease. And so it's save some time for the doctor.
And so did you, maybe you mentioned this, but did you develop this method or have you tested this method or begun testing it or have plans to test it in other areas outside lungs? For instance, like your cover slide, one of your first slides covered a fundus photo, which is an area of interest of mine.
My cover. Yeah, so actually we have built the model not only for the lung disease. Mm-hmm. We also have lung nodule. I think it's the very beginning. So for example, in this presentation, I show 9 different applications. And it's also not limited to the classification task, which means you tell me it's wrong, or it's a disease, or it's healthy. That's a classification task. It's also included the detection, like we don't care, we just need the location. And also the segmentation, like give me the all like lesion segmented for me. Yeah, so the model is not limited to the lung nodule. That's the first point. And your question is how to evaluate the model. So what we do is there is a lot of public available data set, and usually they will public release the ground truth for the training data for us to train the model. And then the organizer will hold the ground truth for the test data. And what we do is submit to the website and get the score, and how the model is generalizable to the unseen data.
Sorry, I found myself on mute. Thank you so much for that, Zhangwei. I appreciate you taking the time to answer some of those more in-depth